So, welcome back to our lectures on projective geometry. This time we will deal with projective transformations and with collineations. Both of them are operations that move points and lines in your projective planes around, move them to different places, and also they are defined in a completely different way. They will coincide over the real numbers, and over other fields they will diverge in, I would say, very, very interesting ways. So let me start with the definition of collineation. A collineation is a bijection between, well, the sets of points and lines and the set of points and lines. So it's a kind of automorphism of a projective plane. And, well, under that bijection, points should again be mapped to points and lines should again be mapped to lines. And now comes the important part. Whenever you have a point that is incident to a line, the two images should be incident as well. You already may imagine those collineations are pretty rigid objects. So preserving incidences is a very, very strong property, and let me exemplify that with a simple example. So assume we have a configuration here consisting of some points and some lines, and we define collineation that maps those 4 points to 4 other points. If we have a collineation, it also has to map the lines, and it has to map the lines in a way such that incidences are preserved. So if you take, for instance, this line here, it's incident to that point and that point, so the image of that line has to be incident to that point and that point. So the position of this line is completely uniquely determined. So if you have a point A here and a point B here, and you have tau of A here and tau of B here, then the line, say L here, has to get an image tau of L at the same time incident to both points. And this now happens to all of those lines. So for instance also to this one here. And now look what happens with our next point. So here we have a point that is incident to those two lines. So the image point has again to be incident to the images of those two lines, and so on and so on. And you see, essentially I moved my points and lines around in a way such that all the incidences were preserved. And well, this may seem like a very simple concept, but it carries several surprises. So this concept is way less trivial than it seems at first sight. We will come to that point a little later. But one important thing here, it is really defined for any projective plane. So no matter whether your projective plane comes from a field or it's just a purely combinatorial object, you can always speak about collineations. So for defining a collineation, you don't need a field in the background. Now we come to the concept of projective transformations. And while collineations did not need a field, projective transformations are really defined over a field. So we assume you have a projective plane over a field, so each of the points and the lines have homogeneous coordinates, and now we can define projective transformations in the following way. So we take a matrix. Which is a 3x3 matrix and which is non-degenerate and taken from fields elements. And then we explain how this matrix acts on the coordinates of points and acts on the coordinates of lines. So a point with its homogeneous coordinates should simply be mapped to the matrix times the coordinates of the point, and a line should also be mapped, but now we have to be a little bit careful. Instead of multiplying with the matrix, we multiply with the transpose of the matrix and the inverse of that. And this will be the image of the line. You may notice that I'm in that definition only take the representatives of my elements and not the equivalence classes. But since we have a linear operation here, matrix multiplication is a linear operation in on the vector that it's applied to. It doesn't matter if we take representatives or equivalence relations. So this concept really extends well to equivalence classes. So we can, if we want, similarly speak about projective maps of equivalence classes, which simply would be, in our definition, the equivalence class defined by the image of the representant, and this thing here really is well defined. So, how do projective transformations and collineations differ? Well, our first theorem, and again with the theorem numbers, I refer to the theorem numbers in the Perspectives of Projective Geometry book. First important theorem is, if I define projective transformations in this way, then every projective transformation turns out to be a collineation, and the proof of that is close to trivial. It's essentially using the definition and checking that everything is satisfied as it should. So how does a proof look like? So assume we have point incident to a line, so we can write this incidence relation as the following product, and here I wrote the scalar product in matrix notation. So I take the vector of P, transpose it and multiply it by the line L, and they are incident if this product here is 0. Now we blow up this expression a little bit by inserting something in the middle, which is nothing than the unit matrix. It's just M transpose times N transpose inverse, and well, then we shuffle around by the usual laws of matrix multiplication, and we find that, well, we can rewrite it in that way. So we have separated the M times P and separated the M transpose inverse times L, and you immediately see those are the definitions we got over here, and well, you see immediately this product is satisfied, so the corresponding images are incident as well. So from that we learn a projective transformation is a collineation. So if one of them is more general than the others, collineations are the more general concept. So let's see how that story proceeds, and let's, well, I was trying to draw an image here, and well, as a matter of fact, there is no way in the real plane of drawing a different image than the one I've drawn for the collineation, because we have another theorem here. Over the real numbers, every collineation is automatically a projective transformation. So when you deal with the real numbers, and if I'm doing a drawing here, I'm really mostly dealing with the real numbers. I cannot draw a different picture for a projective transformation and a collineation, because those two concepts really coincide. And the fact that they coincide is actually a deep fact. It's sometimes in, well, a slight generalization, it's called the first fundamental theorem of projective geometry, and the proof is admittedly hard. And you will find that proof in the Perspectives of Projective Geometry book in chapter 5. Here in these lectures, I only will give you a glimpse of the concepts that are relevant to prove this theorem. So one of the main ingredients here is the following. Let us try to define a collineation, and we saw, well, collineations are already pretty rigid objects. So if I map a point, say from here to here, and another one from here to here, and another one from here to here, and one from here to here, I immediately can draw lines and form intersection points, and lines through the intersection points, and new intersection of those lines, and I can continue and continue, and by that construct a grid of lines that cover, for instance, my square here. And it turns out that essentially a collineation is already determined over the real numbers by the image of 4 points, and this is one of the deeper reasons why it is also projective transformations, since we will see projective transformations are also uniquely defined by the image of 4 points. So let me show you how rigid this thing is. Let me move these points here around, and the idea is that the images of the different pixels of that smiley here in that projective transformation can really be nicely approximated by making that grid denser and denser, and seeing where a corresponding point from here goes in the other picture. And well, you should recognize that to do that, and that's one of the next subtleties, you need some continuity arguments and you need some density arguments, and all they go into this thing here. And one way of stating that is to use the following statement. Before I do that, I want to show you something else. So the projective transformation does not only refer to the inner of this drawing, it nicely extends to the entire plane. And I want to show you at least two effects here. So one of them is that you obviously get accumulation points, where your projective map sends points that were apart very close together to a line. That's essentially well, something like the image of the line at infinity that you see here. Another important thing here, I say it is determined by the image of 4 points, but those 4 points cannot be completely arbitrarily chosen. I should make sure that my first 4 original points were really something that people call a projective basis. No 3 of them should be collinear, because otherwise your transformation here, and actually both the collineation and the projective transformation would be a degenerate situation. And so let's move out of that situation pretty fast again. And now I want to show you a few other things that are important and are a little bit more subtle in that context. So for that, we really have to look a little bit closer at that field we are working at. So we are working over the real numbers, and actually it turns out that as a consequence of this statement here and the density of this grid, we get the following thing. Over R, every collineation can be decomposed into a projective transformation and a field automorphism. Now, I told you I want to show you how subtle these concepts are, and now the term field automorphism comes into play. And actually, this statement here that a collineation can be decomposed into a projective transformation and a field automorphism is true for any field. So no matter if we have R up there or any other field, this statement here is true in all those cases. But now again, something special happens with the real number, the real numbers. The only field automorphism of the real numbers is the trivial one. So the real numbers has only one automorphism, namely the identity. Well, since every collineation can be decomposed into a projective transformation and a field automorphism, it happens that the only way this can happen over the real numbers is that it is just a projective transformation. As I said, the proof is not very easy. You need several concepts that come together here. We will skip them here in those video lectures, but it contains one more ingredient I want to exemplify here. The point that it is determined over that the projective transformation is determined already by the image of 4 points is something that holds in general in our book. It is theorem 3.4, and I just want to quote literally from the book. So here you see the proof written in the book, and I just want to show you the ingredients of that proof. And the idea is you want to show that if you have 4 points, and this time you really need the equivalence classes, if you have 4 points in a pre-image space and 4 points in the image space, and no 3 of those points are collinear in both sets, then you always can find a matrix that maps the points of the first quadruple to those points of the second quadruple. Well, so much about R. Let me finish with some notes on other fields. And well, over arbitrary fields, the following thing holds. Every collineation can be decomposed in a projective transformation and a field automorphism. And as soon as the underlying field has non-trivial automorphisms, then this becomes interesting. So for instance, if you have the projective plane over the complex numbers, the complex number have exactly one non-trivial field automorphism, and this is complex conjugation that sends a complex number into its conjugate, and it turns out that conjugation is also a collineation, but cannot be expressed by a matrix multiplication. But admittedly, the situation here is really difficult to visualize because, well, the complex projective plane lives essentially in a 4-dimensional space. So each complex number has 2 real dimensions, so a complex plane has 4 real dimensions, and it's extremely hard to draw pictures. So I was thinking about a situation where I could show you where the subtleties arise, and I was looking into finite fields, and actually the first time something like a non-trivial field automorphism happens is with the field of at least 4 elements, So the field of 2 elements does only have trivial field automorphism. The field of 3 elements only has trivial field automorphism, but the field that arises from taking 2 to the 2 squared, so which has 4 elements, this field has a non-trivial field automorphism. So you remember we did our count at some time that such a projective plane associated to that field altogether has 4 squared plus 4 plus 1 points. And I was looking for a nice picture of that projective plane, and here it is. Here's a cyclic picture of that plane. So you have altogether 21 points, and each colored line here is one of the lines of that projective planes. So it contains 5 points here. So 1, 2, 3, 4, and 5. And I really urge you to press the stop key and check this diagram. And it really turns out that between any pair of points you really have a unique line here. And now the reason why collineations and projective transformations differ is that by just doing join and meet operations, you cannot get from arbitrary 4 points here to all of the points. And I want to show you that. And for that, I was picking 4 points in that picture. So you see, you have 4 selected points, and I really chose them randomly when I prepared that lecture. And to get a kind of better overview, I diagrammatically draw what I'm doing also on that time. On that side, I really chose 4 points. Now, any pair of those points has a connecting line. So for instance, take this point, and you see this here is the line connecting them, and on that line there are 3 more points. We'll come back to those points later. So we took 2 points and added a line here. So we can take the join of this point and this point and this point of this point as well, and get all together 3 lines, and you see them here in this picture. So we still can do more join operation on these things, and so I add them to my drawing, and now I can do the same thing as before and ask, well, I've now added all together 6 lines. How about the points of intersection of those 6 lines? So we are looking on that circle here for situations when 2 of those lines meet. For instance, here and here and also here. And we see if we fix those 4 points by a collineation, then the lines are fixed and also those 3 points. And now one could hope that one could go on and go on and go on, and at the very end would have fixed the entire projective plane. But something different happens here. So if you look at those 3 points here, they already lie on one common line here, and there is no way of extending this picture further by just doing join and meet operations. This is different from what happened in the real projective plane. There we always could continue and form and create new points, new points, new points. Here, after creating 7 points, we are stuck. And actually what we discovered is that a nice little Fano plane is sitting inside this bigger projective plane. And actually, for any arbitrary choice of 4 points, you get an associated Fano plane in this bigger picture. And well, a collineation at that point doesn't tell you anything more about the images of the points that are not yet covered. So there is some more freedom. You can fix one more mapping, and this essentially corresponds to a field automorphism. I hope that these sketchy words somehow give you an impression of what's going on in that context. And after such deep theoretical investigations, let me end this lecture with something extremely practical. Let's talk a little bit about projective transformations over the real numbers in the standard embedding, and I just want to give you the information that all the usual Euclidean transformations, moving things around, rotating things around, and even perhaps affine transformations, can be found within the projective transformations. So this form of a matrix leads to a translation. This form of a matrix leads to a rotation about the zero vectors. If you combine those two types of matrices, you get rotations and translations. And if you want to have general affine transformations, you can take a matrix that has a unit vector in the last row, and by that leaves the line at infinity invariant, and by that maps parallels again to parallels. And if you go to full generality here and add arbitrary letters in the last row as well, you end up with fully general projective transformations. So I hope that I could give you an impressions of the importance, both from a theoretical and from a practical point of view, of both collineations and projective transformations. And this concludes the slot on projective transformations.